Good evening, all. Welcome to the week 3 live session for the course Matlab Programming for Numerical Computation. Let's wait for 2-3 minutes to see if there are more students to join the live session, and then we'll start the class. So just wait for 2-3 minutes. So let's begin today's session. So this week, as we used to do in the previous weeks also, the first session, I'll do a quick recap of what was discussed in this week. So you can ask questions to me in case if you've gone through the recorded lectures. If you have some questions, you can ask me all those questions. And we'll look at the codes again. And then later we'll solve some problems which are similar to the assignment questions that you'll be getting this week. So that will be like a practice session for you. So let's go to today's contents. So basically, this week, we were seeing concepts like error, machine precisions. We talked about like local error, global truncation errors, and all those terms. So first, I'll just start with explaining to you what machine precision is. So every instrument has something called as a least count. That is the smallest value that can be measured by that particular instrument. For example, if you have taken the ruler or the normal scale that you use, the least measurement that you could take is 0.1 centimeter. So if the actual object you have has a size which is less than 0.1 centimeter also, even with a ruler, you cannot measure it accurately, right? Because the scale starts from 0.1 centimeter. So that is the least measurement that can be taken by a particular instrument. That is called as a least count. So even the computers also have a least count. So that least count that is associated with the computer is called as a machine precision. And the machine precision for real numbers depends on the number of bytes to store a real number. For example, like normal numbers, we have like 4 bytes, and doubles, we have like 8 bytes. So so the number of bytes is associated with the machine precision. So in MATLAB, if you want to know what the machine precision is, there is like a keyword in MATLAB. Just give me a second. Let me just share MATLAB. I hope you can see my MATLAB screen. So in case you want to know what's the machine precision that has been used in MATLAB, we'll just type that the command is called as EPS. If you don't know what EPS is, just type help EPS. EPS is a spacing of the floating point numbers. That is the minimum spacing between floating point numbers. For example, you can see this number is like this, right? 2.22 e raised to minus 16. Okay, let me add a smaller number to it. See, you'll still get 2.44. It'll be still in the order of e raised to minus 16. Okay. Uh, I'll just add something like this. Okay, this is different. But anyways, so this EPS that you can see, there are different kinds of like EPS. So EPS, if you directly give an X number, it's like the positive distance from the absolute X to the next largest magnitude of floating point. Okay, so that is like as you see 0.1 here in Matlab, the spacing is of the order of 2.2204 e raised to minus 16. Okay, below that also, like if you're trying to measure something, what happens is there is like something called as round off errors that will arise when you're trying to calculate with a precision which is lesser than this e raised to minus 16. So this is associated with the Matlab machine. So EPS with no arguments, it is a distance from 1 to the next larger double precision number. So if EPS with no argument, it is equal to e raised to minus 52. Okay, so let's see what is e raised to minus 52 is 2e raised to minus 52. That is exactly similar to your EPS value. So that is the floating point numbers spacing between the two floating point numbers, the least spacing between two floating point numbers that has been encoded in Matlab. Okay, so in Matlab, you can see for a double precision number, it is 2.2204 e raised to minus 16. For single, it is 1.1921 e raised to minus 07. Okay, so that's about machine precision. Now we have seen like several series in our previous weeks also, and also in Max, you would have studied all this Taylor series expansion and everything. So for Taylor series expansion, if you want to compute a function value at a new point, x plus h, okay, imagine that you know how the function behaves at x, okay, and then you need to understand how the function, what is the function value at a higher point, that is at the function at x plus h. H is like a small step size that you take. If that is the case, we can approximate the function value at x plus h using the Taylor series expansion. And how does the Taylor series expansion come? That is f of x plus h is the step size, plus f dash of x. This is the first derivative of the function at the point x, plus h square by 2 factorial f double dash of x. That is the second derivative of the function. And then you have to take the second derivative of the function, and then you have to substitute the x value. And so on, you can have like the higher order terms. Higher order terms means like this is h, this is h square, then you will have h cube by 3 factorial, and so on. This is h raised to n by n factorial, and so on, it goes on. Okay. And finally, there will be like an extension term that is of the order of h raised to n plus 1. Okay, so if we are calculating, if you're trying to calculate the function value using this term, depending on how many terms you're taking, if you take the first term, the answer, just the f of x answer will not be that accurate. But if you just include this term also, h plus f dash of x, your answer will be more accurate. So the more number of terms you add, more accurate your results will be. Okay, and lesser will be the error. So, like something that is error that is associated with how many terms that you take for approximating a particular function is called as a local truncation error. Okay. So here what happens is if I'm truncating it with here at this h raised to n by n factorial, then the local truncation error is order of n plus 1. This order might be a bit confusing to understand at this point of time, that I'll explain later. So accuracy depends on how many terms are used to derive a numerical scheme. Now we'll try to understand what does this order means. Okay, so let's do a bit of derivation. This is not there in the recorded lectures. I hope this will help you. So this is a Taylor series expansion that we have. That is f of x plus h is equal to f of x plus h f dash x plus h square by 2 factorial f double dash x, so on till h raised to n by n factorial f of nx plus order of h raised to n plus 1. So let's bring this term here. Okay, so let me just annotate. Okay, let us bring this term here okay, to the other side. Okay, when you bring to the other side, you will see, okay, I'm only using till n terms. This is the only term I'm using to calculate. To approximate, I'm only taking the first n terms. So then this, what happens is you will be getting a expression like this. This is the actual value at x plus h, and this is the approximate value of at x plus h, right? So this is approximate because I'm not taking like to n up to infinity. I'm not doing that. I'm only taking the first n terms. So this becomes an approximation, and this is the actual value. So what is the difference? What do you call this term? The difference between the actual value and the approximate value, that is called as error. Okay, error associated by using this numerical method. So the error between the actual value and the approximate value, you can say that it is equal to order of h raised to n plus 1. Okay, so this is a power. This is there in the exponential term, right? So what do? You take log on both sides. When you take log on both sides, it becomes log of error is equal to log of order of h raised to n plus 1. So now you know that this term can be taken outside the log. Okay, so it becomes, yes, do you have any questions? Yeah. So you know that this, just a second. So you know that this term is on the power term, so you can bring it back. You can bring it outside the log. So once you bring it back outside the log, it becomes log error is approximately equal to n plus 1 log h. Why is it approximately equal to? This might have some more constant terms like n factorial, n plus 1 factorial, all those terms will be there. But the thing is, as you know that when n is very high, n plus 1 factorial, it comes in the denominator, which means it's a very, very small value. Okay, so it will not be exact. You can't put equal to sign here, but it will be approximately equal to. Okay, so that is why n plus 1 is taken outside, and then you have log h here. Now what happens? Imagine you have like different h values. What is h? H is a step size that you take for this numerical method. So suppose you have different h values and the associated error values. What do? You calculate the log of those h values. You calculate the log of the error values and you plot it. Okay, when you plot it, what will happen is you can see this is an equation of straight line, right? This is a slope of the equation of the straight line. If you're plotting log of error versus log of h, you will be getting a straight line whose slope will be n plus n. Sorry, n plus 1. And in the n plus 1 slope, you will be understanding what is the, so this n, the slope of this curve will tell you the order of accuracy of this method. Okay, so what we say is that any numerical method you have, what you have to do is change the step sizes and calculate the corresponding error values. And then what do you do? Calculate the log of the step sizes and log of the error values, and then you plot them. When you plot them, you will be getting a straight line, and the straight line will have an associated slope to it. Okay, and that slope will tell you what is the order of accuracy for that particular numerical method. Okay, so order of accuracy, we'll do a few examples, so you'll understand physically what does that mean. But I hope that now we have understood, like for a particular method, how to calculate it. Okay, we'll come across this derivative, this definition again and again while coding. We'll see that then. Okay, so now we have seen a special series which is called as Maclaurin series. Maclaurin series is a different version of Taylor series itself. So in Taylor series, you have to take the function to be e raised to x, and the x has to be 0 and a has to be h, the step size. So in that case, if you take the f of x to be e of x and take this all conditions, then the Taylor series reduces to the Maclaurin series. So finally, this is the expression that you get. A raised to a is equal to 1 plus a square by 2 factorial plus a cube by 3 factorial plus and so on a raised to n by n factorial. Again, you will see that it is having an order of accuracy a raised to n plus 1. This is similar to the Taylor series, okay? H is equal to a, right? So obviously, you will be getting O a raised to n plus 1. O a raised to n plus 1. So that will be the Maclaurin series that you have. So what is the error? Error is the difference between the true value and the approximate value. You always have to take a mode because error means it could be a positive error or a negative error. Okay, just that with the term error, we are only thinking about how much deviation is there. Whether it's a positive deviation or a negative deviation, we're not worried about that. So that is why we always take the mode or the absolute value of the difference between the true value and the approximate value. And as I said in the Taylor series expansion, the more number of terms that you include, lesser will be your error. more better will be your approximation. So that is applicable here also. So the more number of terms you take, lower will be the error of the Maclaurin series. Okay, so let's see something. Let's see how to code this Maclaurin series. Just give me a second. I hope I'm sharing Matlab. So right now what we are doing is I'm taking first five terms of the Maclaurin series, and my A value, it is the A value, it is like e raised to A is the problem that we are trying to solve. So A value is equal to 0.1. And as you know, in the Maclaurin series, the first term was 1, right? If you go back, you will see what we are trying to find is e raised to A, and the first term in the series is 1. And the rest you have a raised to 1 by 1 factorial. So this one can be assumed as a raised to 1 by 1 factorial. Okay. So this is a raised to 2 by 2 factorial and so on. So now going back to the MATLAB. So this is the first term. Okay. First term is 1. So the current term is 1. I think I have like declared it twice because I need it for the loop that way. So the current term is 1. Then what I do is I run the loop for 5 times. Okay. So what happens is, what is the current term? The current term is 1 plus A by I. Okay, so that becomes my exp val, and so my next ex, so the current term is already here. Okay, so which means my first, just a second, let me just confirm the expression is right. Oh, okay, sorry, this is calculating the factorial. Okay, so basically what happens is, I'll just type the current term here. So first value will be, okay, first value will be 1 here. So what happens? First value of current term is 1. Now current term multiplied by A by I. So that will become current term multiplied by, it will become 0.5 by I is what? I is 1, right? So I starts by 1. So that will be a second term. So next term will be again this current term multiplied by A by A. So that is 0.5 multiplied by 2. So if you carefully observe, this is 0.5 square divided by 2 factorial, right? So this is how I'm calculating current term. There is better way to calculate this, but right now in the loop, what you can do is, the current term, you can always keep it multiplying to the previous current term. So this will give you each and every term. So first, initially, it will become 0.5 by 1 factorial. Next current term will be 0.5 square by 2 factorial. Next current term, again, you have to multiply one more time. So it will become 0.5 cube by 3 factorial. Okay, it will be like that. So you have got different current terms which has to be summed up, right? Only then you will be getting the entire series. So you're summing it up to the previous sum. Okay. So first what happens? First term only has 1. To 1 you're adding 0.5 by 1 factorial. So that has been already summed here. Then you're adding to that you're adding 0.5 square by 2 factorial. You have already added it. And next time you are adding to the sum 0.5 cube by 3 factorial. It goes on 5 times. Okay. Now what happens, this is a true value. True value means it is e raised to a is 0.1, so exponential of 0.1, this is a true value. Now let's calculate the error. Error is absolute difference between the ABS takes the mode value, okay? Absolute difference between the true value and the EXP value, the experiment value, okay? So let me just clear all the drawings. We'll see it, run and see what is happening in this code. So now if you see, for I is equal to 1, the current term was what? Current term was, yeah, it was Oh, sorry, it was 0.1, not 0.5 when I explained it here. So the current term is 1. Current term is again 0.1 divided by 1 factorial. And you'll be seeing the first term is 1 and the second term should be the sum of it. So that is 1 plus 0.1. Okay. In when I is equal to 2, the current term is this 0.005. What happens? You have to add. So earlier sum was 1. It became 1.100. Now to this you have to add the current term. So it will become 0.105. Now when I is equal to 3, this is your current term. Okay, this current term has to be added again. So initially it was 1, it became 1.1, then it became 1.105, and the next term becomes 1.1052. And again it goes on, and finally what you see is actually this exponential, in the printing you'll be only able to see these many precision. Let's open it here. Okay, when you open it here, what happens is there is like 1, 1.1, 1.1050, 1.10502. After this, what happens is the addition happens in the next decimal places, which are not visible to us. There are like minute changes, but it is not visible. So now to understand the minute changes, what happens is let's calculate the error value. Okay, so the error has been already calculated. Okay, in the first case, the error between the actual value and when you use just first term, that is 1, this is the difference you have, 0.1052. Then next, when you use two terms, that is the first two terms, 1 plus a by 1 factorial, when you use that, this is the error. So you can see the error initially it was of the order of 0.1, now it became 0.0052. Now again, if you look at here, it became of the order of e raised to minus 0.04. So if you're just writing it in the order, let's write it in power terms. Okay. So the first term is 1 point something, 1.052 into, and e raised to minus, zero 1. Isn't this thing? 1.052 e raised to minus 0.1. Next is 5.2 e raised to, this is what, minus 3. And then you have 1.7 e raised to minus 0.4 and so on. So now you can see how the error has been propagating. So initially the error was like very, very high. Now then error became very less. You can see how the order is being getting lower. So it became 0.4, it became 0.6, 0.8 and 0.9. Okay, so that's how the error goes down. So the more number of terms you use, yes, is there a question? Why that error comes minus 2 is 2 terms, please show. I didn't understand your question. Ajit, why that error comes? Are you talking about when I is equal to 2? Okay. Are you talking about I is equal to 2? Ajit, why that error coming for all? Okay. So the thing is, what happened is, I'm calculating the error between the true value and the exponential value. Okay, what is the true value here? I'll just type the true value. Uh, True value is this, that is exponential of 0.1. It is a scalar quantity. Now let's type what is exp val. Exp val is a vector. Vector means this is when you are only using the first term. First term is what? 1. This will be the approximation if you are using the first two terms. That is 1 plus a by 1 factorial. When you're summing both that up, you will get this term. When you're using three terms of the approximation, this is 1 plus a by 1 factorial plus a square by 2 factorial. This is 1 plus a by 1 factorial plus a square by 2 factorial plus a cube by 3 factorial. So this is the different sums. What happens when you are adding more number of terms to your approximation? This is one term, this is two terms, this is three terms, and this is four terms. So now I'm taking a sum, then I'm taking a difference between the true val and exponential, so experimental value. So just think that this is a scalar and this is a vector. You can just do a subtraction. When you do subtract, what happens is this scalar will be subtracted from each of the elements of this vector. Okay, so from each of these elements, 1.1052 will be subtracted and you're taking the absolute value, which means you're taking the mode of the difference. So that is why your error becomes a vector. Okay, this is the error associated when you're using one term. This is the error associated when you're using two terms in the approximation. This is the error associated when you're using three terms in the approximation. That is why you get different error terms. Okay, you can see that right now in the printing, it's just 000. Actually, there are more numbers to it. So if you want to see that, just go click error in the workspace and you will understand. See, the error is like it's not exactly 00, it's just that it's a very low value. So here it is 0.1052, but when you're using more number of terms, the error reduced. It became 0.0052. Again, further on, when I'm using more number of terms, it became the order of e raised to minus 04. Again, when I'm using four terms, it became e raised to minus 06, so on. So the takeaway from this is that when you have like some terms like this, the more number of terms that you add for approximation, more accurate your result will be. Okay. So this is like an infinite series, right? So you have to stop it somewhere. So stopping it somewhere is called as a truncating it. Okay. So when you truncate it, there will be a small error. For example, if I'm truncating with four terms, I'll have an error of e raised to minus 06, right? The small error that is associated when you're truncating a particular expression is called as a truncation error. Okay. And the truncation error, what happens? It will be less if you are using more number of terms. Do you have any other question? Is your question answered, Ajit? Yeah. Okay. So that's how you use Maclaurin series. So the Maclaurin series, this is using a for loop. So I specify that, okay, I have to run it for 5 times. If I want, I can run it for 10 times also. If I run it for 10 times, what will happen? You will see there are more errors. See, minus 4, minus 6, minus 0.8, minus 9, minus 11, minus 12, minus 13, minus 15. It can go up to minus 16. So this is like very, very accurate to the true value. So you can increase the number as per your wish according to the for loop. Now what you can do is the same expression. Okay, right now I wrote it using the for loop. You can write it using a vector. You can write it using the vector operations, the array operations. How do you do that? So I'll just explain this quickly. You know that n is equal to 5, a is equal to 0.1. So what you have to do, this we have repeated it in the previous weeks also. When you have an expression like that, how do you reproduce it? First, what you have to do is, let me just run this. Let's create a vector of the, let's create a vector 1, 2, 3, 4, 5. Do you remember anything here? So this 1, 2, 3, 4, 5 comes in the power. It also comes in the denominator as factorial. All right, because it's a raised to 1 by 1 factorial. It is a raised to 2 by 2 factorial, like that. So this numbers comes in the power and also in the denominator. So let's first calculate the power. How does we calculate the power? It will be a dot exponential. So this is element wise exponential, the vector value. So that will be, this will also be a vector. This will be a vector like, this will be a raised to 1, a raised to 2, a raised to 3, a raised to 4, and a raised to 5. As I know, a is equal to 0.1. So this is what this vector comes. And then you have cumulative product of the vector. What is the cumulative product of the vector? That gives you the factorial, if you remember. Cumulative product means if you have 1, 2, 3, 4, 5, the cumulative product of this vector is, first is 1, next term will be 1 multiplied 2, next term will be 1 multiplied by 2 multiplied by 3, and next term is 1 multiplied by 2 multiplied by 3 multiplied by 4. So that is 1 factorial, 2 factorial, 3 factorial, 4 factorial, and 5 factorial. So see, 1, 2, 2 multiplied by 3, 4, 4 multiplied by, sorry, 2 multiplied by 3, 6, 6 multiplied by 4, 24, and 24 multiplied by 5, 120. So these are the factorials. So we have got each terms. How do you do the each terms? You have to take the powers and you have to do element-wise division with the appropriate factorial. So now we have got all the terms. Then you have to just take the sum of the terms. Remember, we missed the first one. 1 plus a by 1 factorial, right? So we missed the 1. So you have to add that separately. So this is the approximate value that you get from the Maclaurin series. Again, you can calculate the error. This is a true value exponential of a. This will be the error. True value minus the exponential value and taking the absolute difference of it. Did you understand how to write it using this vector? Do you have any doubts?
No, ma'am, not.
Okay. So then what do we do is, let's see this Maclaurin loop itself. Let's see how the error is being changed. Okay. When
Ma'am,
you are
one
yeah,
question here,
yes.
like when you are giving that I value, like I going to one to length all, so anywhere we are not incrementing the I, right? Like I is equal to I plus. So by default, it is going to the next value.
Yeah. So when you're typing in for loop, when you type I equal to, so here I have to done. So here I have done I equal to 1 to n, right? So n is equal to 5. So automatically what happens is Matlab will take first I value to be 1, next I value will be 2. It will be incrementing by a step size of 1. Okay, so it will go 1, 2, 3, 4 till the n value, that is 5.
Okay, and here if I give exponential value I and exponential is equal to exponential value I minus 1 plus current term, will it be same?
I minus I.
Exponential value I minus, sorry, exponential value I equal to exponential value I minus 1 plus current term. So,
No, exponential value. I is the index number, right?
no. So here you have written exponential value I plus 1 is equal to exponential value I plus current term, right? I'm
Yeah.
saying if I write exponential value I equal to exponential value I minus 1 plus current term, will it be same?
Uh, exponential value I minus 1 by current term. No, then
Plus
the
current.
yeah, no, the current term will change, right? So this current term also I you have to change accordingly. So it
Okay,
has to
okay.
be
So
I minus 1.
minus 1. Okay.
Yeah.
Got it. Yeah, thank you.
If you make here I minus 1, then here also you can make I minus 1. You can make it here I.
Okay, and by default, it will go from one to like whatever steps we
Yeah.
gave to n. Okay, fine.
If you want other step sizes other than 1, if you want
Then
a step
one
size
is
of
to
2,
two is one is to two is
uh,
to yeah. That
yeah,
you yeah. Okay, thank
this is what you have to do. Yeah. By default, it will be 1. Okay, now we have to see how to plot. As I said earlier, I said, right, if you are able to plot the step sizes and the errors, you'll be getting a straight line. And from the straight line, the slope will give you the order of accuracy. So that's what we are trying to see here. So far we only used one step size. That is, in the previous Maclaurin series, I said that H is equal to A. H is a step size. A is the A. Here, when you substitute in the Taylor series for H, when you substitute A, you get the Maclaurin series. And then the function has to be f of x, and the function has to be exponential of A. So here what happens is, so far we only checked with one value of A. Let's keep changing the different values of A. For example, here, when you did A for n equal to 5, A equal to 0.1, error was of the order of e raised to minus 0.9. Let me make smaller a. Okay. Now what happens? It became e raised to minus 50. So that means when I'm taking a smaller step size, my error is also decreasing. So there are two things. When I'm increasing my number of terms that I'm adding in the series, more number of terms, lesser is the error. Okay. Lesser is the step size that I take, then also my error will reduce. Okay. Higher number of n, lower is the error. Lower is the step size, then also lower is the error. Okay. So there are like two things you have to keep in mind: the number of terms that you take, and also the step size that you take in such expressions. Okay. So let's see how this behaves. So here what happens is I'm only taking up to 3 terms. Okay. And I'm taking different values of a's. That is different values of step sizes: 0.1, 0.05, 0.02, 0.01. So that is in the decreasing order. I'm taking different values of a's. Now what happens is I'm using the same expression. Okay. These expressions are the same, which I showed you earlier. The only thing is I'm looping over different values of a. I'm looping over this vector. Okay. A length of A all means it goes till how many, what is the length? 1, 2, 3, 4. There are four indexes are there. So it will go from 1 to 4. And first, for the first loop, A will take the first value of A, that is 0.1. In the second loop, A will take 0.05. In the third loop, A will take 0.02 value, so on. So for a particular value of A, the same expressions we use. Okay, the same expressions we use for a particular value of A. We have calculated the particular value of A, we calculate the error, and the error I keep saving it here. Okay, I'll just show you clear CLC. You understand that when I calculate this exponential value, this is a vector, right? This is a vector. True value is a scalar. So this is also a vector. Okay. And that I'm adding a semicolon and then I'm adding it. So basically what happens is I'll get a value like this. See, I'll get a value error like this. I'll get different plots. I'll come to that later. But error I'll be getting like this. There are 4 rows and 3 columns. What happens is in the first row, I got a error. True value minus exponential value. That is this. And in the second value of A, I put a semicolon and I add it. Semicolon means it will go to the next line. So this is for the second value of A. Again, semicolon, I'll be getting for the third value of A, this is the error. For the fourth value of A, this is the error. Okay, so every column corresponds to different values of A's. Now, what is the column corresponding to? Column is when I am using number of band n equal to 3, right? I have used 3 terms. When I'm only using one term, this is n equal to 1, this is n equal to 2, this is n equal to 3. Okay, that is this is n equal to 1, n equal to 2, n equal to 3. First row is a equal to 0.1, second row is a equal to 0.05, third row is a equal to 0.02, and fourth row is a equal to 0.0. This is how the error will look because I am adding my vectors like this. Do you have any doubts? Like how this value has been coming? Is this clear?
Yes, ma'am.
Okay. Now what do we do is we just plot it. Okay. So the first plot is let me run the code again. Already some previous plots are there. I'll have to close all those. If you want to close some background plots, you have to just type close all. Okay.
Ma'am, clear won't do in closing the graphs.
No. Clear is only for workspace. It will
Command.
not clear.
Yeah.
A clear will only clear workspace. If you want to close a figure, either you can type close a figure name. Otherwise, close all. It will close all the background figures that has been there.
Okay.
Just a second. There are 3 figures. Let me just. So I'm getting 3 figures. So the first what I'm doing is I'm plotting all A's versus errors. A values are 0.1, 0.05 till 0.01 and I'm plotting the error. When I plot it like this is what I'm getting. I get 3 curves. Let me just do one thing. This plot is really bad. I'll just increase the line width. This is how the plots look. So the first plot I'm plotting A versus error. So A versus error means A it's a vector, it's a single vector, but error has like four rows and 3 columns. Okay. So right now what happens is so this is also equal to 4. So it will be taking the what you say correspondingly it will be taking 4 y values, right? So that will be taken uh, along the columns. Okay. First line will be this column. Second line will be this column. Third line will be this column. So you will be seeing. So the first line is what? It is for corresponding to n equal to 1. Then you have n equal to 2 and you have n equal to 3. So you will be seeing this value is 0.0052. Okay. This value is 0.00127, which is 0.0013. Okay, this one here. So this blue line is for n equal to 1. The red line is for n equal to 2 and the next line is for n equal to 3. So what happens here? Just think if you're decreasing the step size from 0.1 to lower value, your error keeps decreasing. You realize that error, this is the error bar. Okay. So The lesser is your step size, lesser is your error. Okay, now let's look at the number of terms. When you use the 3 terms, you can see the error is higher. But when you increase the terms to 2, you understand that the error has come down. So more number of terms, lower is the error. Okay, and smaller is the step size, then also lower is the error. Did you guys understand the trend?
Yeah, print
Okay,
function. Yeah, yeah.
yeah. And the next is, I told you that we can always plot the error in a log-log plot. Okay, so there are 2 ways you can do it. One is a log-log plot. This is a Matlab function where your x and y axis will be in logarithmic scale. So I'll show you here. This is a log-log plot. So you can see the x-axis, it is 10 raised to minus 10, 10 raised to minus 9 like that. And this is the step size will also be in log scale. X and y axis will be in log scale. So what happens when you plot in log scale, since you saw that expression, okay, when you convert into logarithmic scale, that expression comes like a linear line, okay, straight line. So that is why you get straight lines. Here again, the first line corresponds to n equal to 1, second line corresponds to n equal to 2, and third line corresponds to n equal to 3. So if you look at the value here, see, again, when you click the value here, you'll be seeing 0.00517. That is this value. Okay, the values will not change, just that it is the scale it is plotted is different. It is plotted in the logarithmic scale. Now, another way of plotting is, why don't I plot the log? Why don't I take the log of the values and plot it? Okay, so that's what it's been said in the expression, that derivation which I showed you. See, you have to plot the log of the error versus log of the step size. Okay, you have got some error value, take the log of it. You have got some step size, take the log of it, and then you plot it. So when you plot it like that, what will happen? You will be getting this plot. Okay, this y and x-axis, just look at the y and x-axis here. See, now this is the log, it is the values are converted into log scale and then plotted. So that is why the x and y axis looks like this. Now what you have to do is you have to calculate the difference, the order. Okay, so for that, what you have to do, you have to just calculate the slope of this line. How do you calculate slope of this line? That will be difference of y values divided by the difference of x values, right? So that will be minus 3.76721 minus 6.77, again 1706 divided by minus 1 minus 2. You will be getting 3, okay, approximately equal to 3. So this is corresponding to n equal to 2, order is equal to 3, okay. When n equal to 2, this curve's order is equal to 3. Again, let's calculate for this line. This is for n equal to 3, right? Let's calculate for this line.
Ma'am,
For
what is
any,
the format when you gave minus 3.76 and you gave
this is
double dot?
y value of the first curve. This difference between this term. This is minus 3.76721.
Yeah, yeah,
This is
that I got. Like,
uh,
instead of subtraction, you gave two dotted. Okay, minus of minus. Okay, okay.
minus this. This is the one
Yeah,
value, right? This is the
yeah,
second
yeah,
value.
yeah.
This is the first value. You have to calculate the difference between y values divided by difference between x values. Yeah. So this is minus 5.37147. And what will be the next value? Minus 9.37934. And that is divided by minus 1 minus 2. Do we get 4? Yeah, we got 4. So when n equal to 2, order is equal to 3. When n equal to 3, order is equal to 4. You find a trend there? Okay, let's go back to the expression. See, you see here, when I'm using n terms, my order is n plus 1. So when I'm using 2 terms, my error is n plus 1. That is, my slope will be 3. If I'm using 2 terms, my slope is equal to 3. When I'm using 3 terms, my slope is equal to 4. You got the value of this n plus 1? So this is what how we will be doing it. If you have given a certain expression for different values of h, compute the error. Then what do you do? Take the log of the h values, log of the error values, plot it. And from that, you'll be getting a straight line. Take the slope of the straight line. That will give you the order. Okay, you understood this thing, the relation. When you take n terms, the error will be of the order of n plus 1. That will be the slope of the straight line. Okay. Let's look at the error value. Yeah. So that will be how the error value looks like. Now let's go back to the next portion. Let me just close all the figures. Yeah. So these are the conclusions that we make. More number of terms, lower is the error. Smaller is the step size, lower is the error. Plot the log of error versus log of the step size. Here in the step size is a itself. We get a linear curve. And the slope will give you n plus 1. The slope gives you the order of accuracy of that particular method. Okay. So now we have talked about all this Taylor series and what you say, the Maclaurin series. Now we have something which we have learned in our lower classes, the numerical differentiation. So you always know that f dash of x can be written as f of x plus h minus f of x divided by h. This expression you already know, but this is an approximation, okay? Because along with this, there are some higher order terms like this, minus h by 2, f double dash of x, like that, so on. So this is basically, you say that it's the order of accuracy h, right? Here you have h here, okay? So, and this term will be, we are assuming it's a very, very small term. So what happens is, we say that this method is of the order of accuracy h, the numerical, the basic numerical differentiation. So nobody had asked me this. Why is it called as what is called as order of accuracy? Order of accuracy means if I'm decreasing the step size by a factor of 10, then my error also decreases by a factor of 10. Okay, if I say my order of accuracy is h square, what happens? When I'm decreasing the h by a factor of 10, my error decreases by a factor of 100. Okay, so that's what's called as order of accuracy. The how it is related to the step size. H decreases by a factor of 10, error also decreases by a factor of 10. So now we have seen about truncation error decreasing with H and machine precision. Okay, let's do some problems related to this. Just give me a second. So this is how we calculate the numerical derivative. The first line, okay, I'm differentiating tan inverse of x. So the actual inverse I'm taking for step size I'm taking is, the value that I'm taking here is 1. Okay, basically my aim is I have to calculate the derivative of tan inverse of 1. Now the true value is what? True value, what is the difference? If you differentiate tan inverse of 1, you'll be getting tan inverse of A. Just imagine this should be A actually here. Okay, I'm calculating tan inverse of tan inverse of A. The actual value is 1 divided by 1 plus A square. Okay, so that is the actual derivative. Now, using the numerical derivative formula, first I'm taking an h value of 0.01. Now, my approximate value in Matlab for tan inverse, the function is A tan. Okay, yeah. So sine inverse, it will be A sine. Cos inverse, it will be A cos. That's how it is written in Matlab. Okay, so what I do is I have to calculate tan inverse of A plus H minus tan inverse of A divided by H. That is a formula, right? Numerical derivative formula. Should I go back to that again? So I have to calculate derivative of tan inverse of x. I have to calculate tan inverse of x plus h minus tan inverse of x divided by h. That is a formula. And I am calculating it for h is equal to 0.01. Error will be the true value, that is this, minus what I get from the approximate value. Now what I do, I take a very smaller step size. Again, I do the same exercise. I take a smaller step size. Again, I do the same exercise. I'll just run and show it to you what happens. I'll run it. Yeah. The true value, where did you get? No, that is a go Google and see what is the differential of tan inverse of x. Just Google and see what is the inverse. These are the trigonometric formulas that you learn. Just Google.
Yeah, it's correct. 1/1 plus x square, right?
Yeah. See, that is an expression. So that is where you got the true value from. Okay. Now I ran the code. Now what happens is when I'm taking h value to be 0.1, 0.01, my error is 0.0025. When I took h is equal to the smaller value, basically this is 1.10 raised to minus 2. This is 1.10 raised to minus 3. Okay. I decrease the h value by a factor of 10. You can see the error also decreased by a factor of 10. So this is what? This is 2.5 into 10 raised to minus 3, right? This one. This is 2.5 into 10 raised to minus 4. Again, I'm decreasing h by a factor of 10. This is 1 e raised to minus 0.4. My error will become 2.5 10 raised to 2.5 e raised to minus 0.5. Again, I'm decreasing h by a factor of 10. My error also decreased by a factor of 10. Okay, did you understand the order of accuracy? So that is how the h and error values are related. If I'm decreasing h by a certain factor, error will also be reduced by that particular, the order of accuracy factor. Okay.
So
Now, yeah,
formula when it was like h square by 2, so that part can you like in the can you go in the formula where you showed like
yeah,
fx plus h minus fx?
it was h by 2.
Yeah. So h by 2. So this part you are saying like this will be like order will be automatically taken.
Order you usually take with respect to this h. This h doesn't have any power, right? So that is
Yeah.
why we say orders h. In the previous term, if you see, this is h raised to n plus 1.
Yeah.
Basically, what happens is, and what is actual next term? Actual next term is h raised to n plus 1 by n plus 1 factorial f of n plus 1 x. That is the next term, right?
Yes.
Whatever comes
From
in the power of h, that's what we take as order of accuracy.
okay. Okay.
Okay, because why we consider like that is because in all the series, the last term is actually a very small terms. Okay, that doesn't significantly make a difference. So we
Hmm.
assume that this can be approximated. That the whole term we can say that okay, let's only take this h raised to n plus 1. You can approximate it that way. It will be
But
very
in the
small.
while in the writing in the MATLAB code, we are not writing this part, right? Order of
No,
H. No.
no. We are truncating it here. No, we are truncating. So
Getting
when you're
yeah.
writing in MATLAB code, you have to decide till which term you have to take. You don't
Okay.
have this term. You only
So
truncate it with it.
if I try to generalize the formula without knowing the till which order I have to go.
So that's what I'm trying to say. Okay, that's the next point that I was trying to say. Now we have
Okay.
understood that more number of terms we add, lesser will be the error. Okay, does that mean that I can go up to infinity and I'll be getting approximately, I'll be getting the exact value? Is that true like that? So for that, what we do is this term, right? This thing, we'll put it in a loop. The loop will be running for 2 to 7, it will be running for 7 times. So what happens is I'm changing the h values. Okay. So my h value will be 10 raised to minus 1. So minus I. I will be taking initial loop, I will be taking value 2. So this is 10 raised to minus 2. Next it is 10 raised to minus 3. Next value will be 10 raised to minus 4 and so on. This is the approximate value. For a particular h value, I calculate the approximate value. This is a true value. I calculate there. Then I save the h values here in this vector and error values also in this vector. Okay. Now let us see. Now what I do is I plot the log of it. Okay, log of h and log of error values. Sorry, this is log plot, but you'll be getting the similar trend. If you want to plot, you can plot log of this versus log of this. But I'm just telling you I just want you to show the slopes. Okay. So I'll run this here. Okay. This is h And x-axis you have h values, y-axis you have the error values. Okay, so smaller the h value is, you understood the error is also decreasing. This was h. Okay, when h is equal to 10 raised to minus 2, error is very high. When h is equal to 10 raised to minus 7, the error is very small. Okay, you can see the error value is decreasing. So the more number of terms that I'm using, sorry, no, not the more number of terms. I'm sorry. First, I'll discuss about more the step size. Okay, the smaller the step size I'm using, smaller is my error. Okay, so let me make the step size even further small. Okay, so now I'm using 40. The step size is 10 raised to minus 40. When I do that, again run the code here. Okay, you can see the plot becomes like this. Okay, this is true for number of terms also. Though ideally we say that if we decrease the h value or if we increase the n value, you will be getting maximum accuracy. Okay, that is not true practically when you code it in Matlab. Why? Because up to a certain extent, you will see that the error decreases. Then after a point, you will see that the error is increasing. That is because Matlab has a precision associated with it. Beyond a certain point, Matlab cannot accurately give your values. Okay, so beyond a certain point, something called as round of errors comes, which is associated with the machine precision. So you can only go up to like maybe 100 terms, 200 terms, depending on your problem. But beyond that, you can't keep on increasing your step size, and you can't keep increasing your number of terms, and you can't keep decreasing your step size. Okay, so whatever is practically feasible, only do that. Beyond that, you'll not be getting accurate results when you code it in MATLAB. Okay, does that answer your question? So what you do is if you have some approximation in your
Yes, ma'am.
system, code it for maybe like 100 times. So basically what you can see is you run the loop for 50 times. See the error values. If the error is like 0.0000, like up to like e raised to minus 10, then there is no point in running it 100 times. Okay, that 50 was good enough. So depending upon your problem, you do some optimization. Like see how many times I have to run the code. If the error is negligible, you don't have to run it any further. So in that case, using while loop is very, very good. Okay, instead of in the loop explicitly telling that let me run it for n times or let me run it for 10 or 15 times, what you do is you put a while loop and say that if the error goes below this threshold, like e raised to minus 5 or e raised to minus 7, okay, then I'll stop running my loop. So it's not the number of iterations that is important. Let's look at the error value. And if the error is negligible, then let's stop the iteration. Let's stop using the formula. Okay. Is that clear? I think,
Yes, ma'am.
yeah. So the next question you will understand. So the next topic is, the next topic is actually iterative method. So this uses a while loop, which I told earlier. So in iterative methods, what happens is, these methods are called as fixed, like direct methods. Okay, direct method means one formula will be given. You can put the values of these variables in the formula, and you'll be getting the answer. So this is a direct formula. Huh? Now there are some iterative formulas. Iterative formulas means for calculating square root of 2, there is a formula like this. Xi plus 1 is equal to half of xi plus 2 by xi. So what happens is to begin this method, I have to first guess the value for x. So I'm telling that let x be equal to 0.1. So what I do is I put 0.1 here, okay, in the left-hand side of the equation, and I get a value that is half of 0.1 plus 2 by 0.1. I get some value, right? That will be my new x. Again, put the new x here. I'll be getting a newer value for x. So this keeps on going. Okay. When do I actually stop? I actually stop when I realize that the new x values are giving me is almost the same. Okay. You know the square root of 2 is 1.414, right? After a point, you'll realize that it will be 1.4141, 1.4111. The values are hardly changing. So basically what happens is in this case, you will be taking an error between the current value of x and the previous value of x. That is x of I plus 1 minus x of I. When this error is very, very small, that is, you are doing an iterative computation, and in like subsequent iterations, you realize that error is very, very small. Then what happens? We say that, okay, this algorithm has converged. And whatever X you're getting right now is the right answer. Okay, that's how you assume it. I'll just show you how to code this thing. This is the Heron's algorithm. So either you can use a for loop or a while loop. So for loop is pretty straightforward. First, I'm taking X value. I'm guessing it to be 0.5. Then I'm running it for 3 times. My new X value is half of the old X value plus half of X plus 2 by X according to the formula. Then I calculate the error. Error is what? Error is the difference between my new X value and okay. So the new X value, difference between the old X value and the new X value. Okay. So that is a difference, error difference. And then I substitute to the old X value, I substitute the new X value so that the loop can continue. I have to update the value of X. So the X value is updated. Now I'll just run this loop. Okay. What happened is I'm running the loop for 3 times. Initial X new was 2.25. So the error means the error between 0.5 and 2.25 was 1.15. Okay. Now the new X value is 1.5694. The error between the 1.5694 and the previous value, that is 2.25, was this error. So like that, when I go, I'll realize that I think I just ran the whole code. Let me just see. I just wanted to run this section. Yeah. This is my new X value. This is my error value. My error value is higher, 1.75. In the next iteration, my X value got updated to 1.569. Now the difference between these two values are 1.6806. It is lesser. Again, my X got updated. Now my error again dropped to 0.1476. It keeps on dropping like that. Okay, let me run it for some 20 times and let's see what the error value is. See, after running it for 20 times, my error value is e raised to minus 10. And what is my X value? Let me just see. My X value is 1.4142, which is equal to square root of 2. So if you want to run it using for loop, you can do it. But the problem is you will never know how many times you have to run the loop. So the better way is to use a while loop. So in a while loop, what I do is I keep a tolerance level. I say that my error has to be below e raised to minus 5. So this is my X value. I'm starting with the guess of 0.5. My tolerance level is this. Now, initially, I'm just declaring my error to be a pretty high value. It has to be greater than this value so that my loop can start. Okay, then this is like a counter to make sure that how many times I've ran the loop. So let me just clear all this. Okay, now what happens when error is greater than the tolerance level? Okay, 1 is greater than the tolerance level. So I'm entering the loop. I'm just counting how many times the loop is running. Okay, my old X value is half of X plus 2 by X, the formula. Then I calculate the error, absolute difference between X and the old X value and the new X value. Then I update the X value. Okay. So let me run this. I ran and the loop ran for 6 times. Loop ran for 6 times and I get the error value of 1.5184 e raised to minus 10. What is my X value? X value is 1.4142. Okay, what is my new X value? That will also be the same. See, 1.4142. See, that's how we use a while loop. You can keep a tolerance level and you can run so that Matlab itself will identify when to stop your loop. Okay, instead of a for loop, you don't have to decide how many times you have to run it. You can use the same theory in other series also, in other the Taylor series expansion also. So if you want, you can just run it until the error value goes below a certain iteration, so a certain value. Okay, is it clear? Any doubts?
Mm.
Okay. So we have seen iterative methods. Next is called a stepwise method where there is error propagation. So we have seen Taylor series, right? We have seen one-time application of Taylor series. For example, if I have to calculate what is exponential? So this is Taylor series, right? E raised to x plus h is equal to e raised to x plus h plus e raised to x. It goes on. Again, you can have h square by 2 factorial e raised to x. And it can go on like that. Okay. So this is a Taylor series expansion for e raised to x plus h. What I do is, if I want to calculate exponential of exponential of 0.01. Basically, if I have to calculate this, okay, basically, if I have to calculate this, then I do this Taylor series expansion once. I take h to be equal to 0.01, x to be equal to 0, okay? Then I do e raised to 0, 1 plus h. This is one-time application of Taylor series expansion. I'll get this value, okay? What if I have to apply Taylor series expansion like repeatedly? For example, my aim is to get e raised to 0.1, okay? I have to start my calculation from e raised to 0. So directly if I calculate, I'll have to take a huge step size. H is equal to 1. Okay, all this Taylor series expansion and all, you know that this expansion will be only correct if you're taking a relatively small value of h. That's what all the expansion assumes. Okay, we have to take a pretty small value of h. So here h value is bigger. So what we do is we take from first from e raised to 0, you apply one Taylor series expansion, you get e raised to 0.01. You apply Taylor series expansion again. So you put e raised to 0.01 here, x remains, the step size remains the same. Okay. Then you get e raised to 0.02. From e raised to 0.02, you can calculate e raised to 0.03 with the same step size, right? So like this, if you go, you can go from 0.01, 0.02, 0.03. Finally, you'll be landing 0.01. Okay. This is when you're using two terms of the Taylor series expansion. What if I am using three terms of the Taylor series expansion? That is 1 plus h plus 0.5 h square. E raised to x, you can take it outside. So again from e raised to 0, I compute e raised to 0.01. From that, I compute e raised to 0.02. From that, I compute e raised to 0.03, so on till e raised to 0.1. Okay. Now what happens is, if you have seen the earlier Taylor series expansion, if you only use once, the order of accuracy is n plus 1. Okay. But when you use the Taylor series multiple times, okay, what happens is this expression had some error that will get accumulated to the next expression. That also has some error, and the expression of the error of these two expressions will be getting added to the third one. So what happens is, when you use this expression multiple times, your errors get accumulated from your first iteration onwards. Okay. So that when the errors get accumulated, then that is called as a global truncation error. The other one was local truncation error. We are only using it once. Okay. That is local to that particular expression. But when you are repeatedly using a formula, then it becomes global truncation error. And for Taylor series expansion, the global truncation error order is n, not n plus 1. N is for local truncation. If you are using it repeatedly, then the order of accuracy is n. Okay, not n plus 1. So how to verify this? I'll just do one thing. Just need to clear all the drawings. Okay. How to verify it? Let's see. So what we do is we create a code for it. Okay. So what I do is initially I have like a value 0.1. I'm calculating exponential of 0.1. H I'm taking a very small value. So first let me take 0.1. First I took 0.1 and then I'll take true value of e raised to a. Then for calculating that particular Taylor series expansion, I use this multi-step one function I have written. Okay, let me take this multi-step here. Okay, this multi-step takes two inputs. One is the a value and then the step size value. Then what happens? It has to run for how many iterations? The iterations here right now, my step size is 0.01. Okay, and I have to reach till 0.1, 0.12. Yeah, 0.1 divided by h. That will be the total number of times I have to run it. Okay, because of the step size is 0.01, you have to run it that way. Now I'll get number of times I have to do it. Now I am just taking a starting value e raised to 0. E raised to 0 is what? E raised to 0 is 1. So that's what you have written here. E raised to 0 is 1. So E raised to 0, 1 plus h. Okay. And then the next expression, you will be getting E raised to 0.01. So that will be E raised to 0.01 multiplied by 1 plus h. So on it will go on. And final value will be giving you E raised to 0.1. So that will be the output. Okay. So now from this, you will be getting E raised to 0.1 as per multiple Taylor series expansions. And then you will calculate the error value. So let's calculate the error value here. Let me clear this. CLC. I think I don't have to repeat all this. I'll just type the HN. Just a second. Yeah, am I doing it? When H is 0.1, error is 0.0052. Let me decrease the value of H by a factor of 10. What will happen to the error? Let's see. Okay. This is 5.2 e raised to minus 3, right? It became 5 point something e raised to minus 4. Now again, let me just decrease the value of H. Again, I'll run it. It became, earlier it was minus 4, that became minus 5. Again, decreasing the value of H. Earlier it was minus 5, it became minus 6. So what happens? H, when I'm decreasing by a factor of 10, error is also decreasing by a factor of 10. Okay, so what is the order of accuracy? Order of accuracy is 1. Okay, the slope, it is H. So here, if you see, what is the order of accuracy? Order of accuracy was, just a second. Yeah, order of accuracy is 1. So what is this H raised to n? This is when I was using this formula, right? When I'm only using the first term, okay, then the order of accuracy is H raised to 1. What happens if I'm using two terms? I'm using this term and I'm using this term, okay? Then what will happen? Let's see. So the only thing you have to do is in multi-step, instead of this formula, you have to add this one. That's the only difference. Okay. So instead of exponential value, it has to be multiplied by this expression. 1 plus h by 0.5 h square. That's the only change you have to do. So again, we'll do the same thing. First for 0.1, error is e raised to minus 0.4. 0.2, it is e raised to minus 0.6. 0.4 minus 0.6. Okay, it became 0.6. Again, adding one more 0, it became e raised to minus 0.8. Okay. So earlier what happens when I add, so if I was truncating it here for a single Taylor series expansion, the order was h raised to n plus 1. Okay. Here when I'm using global truncation, what happens? Error becomes order of n. So if I'm using one term, it will be h raised to 1. If I'm using two terms, it will be h raised to 2. Okay, did you understand the difference from the values?
Yes, ma'am.
Yeah. So we have so far in this today's week, we saw what is machine precision. We understood what is the least count. Then we saw what's a true error. True error means that is the actual value minus what you get from the expression. Okay. The current error means that will be the error difference between the current value and the previous value that you got from the previous iteration. So this you calculate for calculating the iterative methods. This is the error that you calculate. Okay, we use true error to analyze the errors and approximation, and current approximation error is used for stopping an iterative method. So this is where you use these different kinds of error values. So, and we saw now direct methods. Direct methods are there for numerical derivatives, and also Taylor series expansion. Have this Maclaurin series. All those are direct methods. Okay, we direct application of the formula. Then we saw iterative methods, which is the Heron's algorithm. You start with an initial guess value for x, and you keep updating it until you find that okay, x is hardly changing. Okay, when you find that, you stopped your calculation. Next is stepwise method. How does the stepwise method work? you have to apply the same formula multiple times. When you apply multiple times, the error will get accumulated. So in that process, what the error you get to be the final error that you get is called as a global truncation error. Okay. Once if you use an expression, it is local truncation error. And if you're using the same expression multiple times, then that is called as a global truncation error. Okay. So that these are the things that we covered in today's week. I think we have almost done. Yeah. So now we are going into the questions. Okay, these are questions that you'll be, these are similar to your assignment questions, so it will be helpful if you're trying to solve it now itself. So what I'll do is I'll give you some time. Just go through the question, try to answer that. If you have Matlab, please try to code them also. If you don't have access to Matlab right now, just take a pen and paper and try to write the codes for this. Because unless and until you practice, you're never going to learn a programming language. So try doing this and let me know the answer in the chat box, and then we'll discuss the answer in like 4 or 5 minutes. Okay, just take your time. And if you have any doubts in the question, please unmute yourself and ask, or just put it in the chat box. So true value is 1 divided by 1 by x, right? X is equal to 0.6. So this expression gives you the true value. And this is the approximation. Okay, so this is what you have to code in the loop or using an array. This side of the equation, you have to code it. This part will give you the true value. 1 divided by 1 minus x. Uh, got an answer. Okay, anyone more with an answer? Okay. So I'll just give you 1 more minute and then we'll discuss the answer. Let's try discussing it. Okay. So you have to code it in Matlab. Let's see if there is a pattern. So for the loop, you know how to do it. Okay, the power, there is a pattern in with respect to the power. It goes from 1 to 1, 2, 3, 4 up to 100 terms. It goes up to like that. So remember in the 100 term, the first term is 1 and the second, then it starts from 1, 2. So if you code up to x raised to 99 also, it will be right. Okay. So now using for loop and using array, just a second, let me share Matlab. Okay. So first using for loop. Okay. So the x value is 0.6 and the first value is 1. And I'm running the loop for 99 times. So the total number of terms will be 100 terms. Now what I do is I is equal to, I'll run it for the 1 to 99. And what will be my value? My value will be the first starting value plus the new value, new term. That will be x raised to I. Then next will be this plus x raised to, the next I will be 2, right? So it will be x, first value will be 1 plus x raised to 1. The next value will be this term plus x raised to 2. Next will be, it will be adding x raised to 3 and so on. So you'll be getting the final value here. So the true value is nothing but 1 divided by 1 minus x. So I'll just run this part, run section. So the actual value we'll be getting is 2.5. So let me just type. Yeah, this is 2.5 that we'll be getting when you're using 100 terms. The same thing can be written using an array. How do you write it? You have to create a vector. So for creating a vector, x is equal to 0.6. Num I'm taking 99 because the first term is 1. Okay. Then I create a vector of powers. The power is 1, 2, 3, 4, so on. So I create 1 to num. That this I is the vector for that. Then what I do, I have to write element-wise exponential. So x dot exponential I. So the first term will be x raised to 1, next will be x raised to 2, next term will be x raised to 3, and so on. So I've created the terms. Now I have to sum it up. I sum the terms. Now I missed the first one, the first number 1. So I add 1 to it. Okay, so this will be my final answer. Again, I'll run the code. The answer is 2.500. Okay, both of you have got it correct. Yeah, good. So I hope you've understood how to work with for loop and while for loop and arrays for such expressions. So there is one more expression here. We have to calculate sine pi by 4. So if you have to get the true value, you have to just substitute here pi by 4. You'll be getting the true value. And this is the expression. So here there is one tricky part which you have to keep in mind. Apart from the power going to 357, you can see the power going for 357, so on. There is one more thing here. You can see the sign is also going plus minus. It's alternating between plus and minus signs. Okay, so you have to capture this one also. Okay, using a for loop. You can do it using a for loop. I'll give you some time and then we'll discuss the answer. Yeah, some person has got the answer. Shankar has got the answer. Any more answers? I'll just give you 2 more minutes and then we'll discuss. Yeah, we've got one more answer. So, okay, let me start the discussion. So, the expression is x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial and so on. Just a second. Okay. So, the x is pi by 4. So, I have to use a for loop. So, what I do is I just calculate, let my initial value be 0. Then I calculate it for like, what is num? Am I using num anywhere? I don't think I'm using. Yeah, my a is equal to 1. So a is basically, have this variable to control the sign. Okay, I'll come to that later. So first what happens, as you seen, the power goes like, it goes from 3, 5, 7, so on, right? So is there a next term also? Yeah. So it goes from 1, 3, 5, 7. So the loop has to be like 1, then 1 plus 2. So it will become 3, then 3 plus 2, it has to be 5. So here the loop has to be incremented by 1 colon, 2 colon. I'm using first 10 terms. So it will become 1 colon, 2 colon, 10 terms. 10 times terms will be there. And my sign val I've declared initially to be 0. And the first term will be, my a is 1. Okay, so it is just, this will be just 1. And then it will be x raised to 1 by, this is for calculating the cumulative product. So this will be, so basically this vector will be having just 1 and it will be the product of it. In the next iteration, this vector will have 1, 2, 3. So it will be the product of it. That will be 3 factorial. So on it will go. So this is the term. I'm sure that this term you would have understood by now. Now, how does the A work? So first, to begin with, your A is 1. In the next loop, what happens is your A is changed to, you're multiplying it by minus 1. So what happens in the next time when you enter the loop, it will become minus 1 here. Okay. And the next time, what happens? Again, it will be minus 1 multiplied by minus 1. So it will become positive. So again, here it will become positive. So what happens? Initially, it started with positive. Next, it will become negative. Again, next, it will become positive. And next, it will become negative. It will alternate between plus and minus signs. And this expression will remain as such. Okay, so that's how you calculate your sign val. This num thing was, I don't think it is necessary. I'll just cut it out. So let me just run the code. The actual expression that you get is actually 0.7071 and the true value is also 0.7071. So let me look at the, yeah, both of you have got the right answer. Uh, Shankar, please don't annotate. Let me just, yeah, yes. So I hope you guys have got the right answer and I hope you guys understood how to code this one. Okay. Now moving on to the next question. So this is like an iterative method. Okay, just like we saw how to calculate the square root of 2. Here we have an expression x square minus 3x minus 5. The root of this expression, that is x, can be found out using this iterative method. Okay, the initial guess of x should be 0 and the tolerance that you take. What is a tolerance? Tolerance means the difference between the xn plus 1 and xn. The difference between this has to be below 0.01. Okay, calculate the absolute error that is below this value, and also, so the absolute error should be below this value, and calculate the number of steps that is required. How many loops have you ran to get this desired tolerance, and find the value of x also. Okay, I'll give you a few minutes and then we'll discuss the answer. Once you've got the answer, please put it in the chat box. I've got some answers. Okay, let's see. Okay, so let's try to code this. The expression is square root of 3xn plus 5. So start with I start x is equal to 0 and my tolerance is e raised to minus 3. The error value, I just take it to be a very large value. We have got some answers. We'll see it. Okay. Yeah. Good job, everyone. So yeah, the first error value, I'm just assuming it to be a very large number so that I can get my loop started. So my first starting, I just declare n equal to 0. Now the error, is the error greater than tolerance? Yes, it is. Now my new x value is square root of 3x plus 5. Okay. Then I calculate the error. Error is nothing but the difference between the new x value and the old x value, absolute error difference. And then I update my x value. I count the number of n. Okay. So this while loop has to go on until my error drops below this tolerance. So I'll run this loop, CLC. Yet finally, the x value should be 4.1925, 1924, and my number of times the loop ran is 10 times. Okay, after yeah, the loop ran for 10 times. So anybody having any doubts? I hope I didn't make any mistakes while calculating. Is everybody getting the same answer? Yeah, 4.1922 to 10 iteration, 10 iterations. Yeah. All right, guys, you're getting this answer correct. And what is the error value also? We'll see. Error values of the order of e raised to minus 0.04. 3.9205 e raised to minus 0.04. I hope everybody have got it. If you have any doubts, please ask. Okay. Let me move on to the next question then. This is the next question. It's a 3-point forward difference formula to calculate the derivative of x cube of a function. Okay. So this is 3-point derivative formula. X cube is the expression. This is how I calculate it. What I have to do is for x is equal to 3, compute the error values for different step sizes. That is for x is equal to 0.01, h is equal to 0.001, h.01, and 0.1 and 1. For 4 different values of h, I have to compute what is the expression and I have to calculate the error value. I have to plot the log versus the step size, log of error versus log of step size, the plot, and find the order of accuracy. Okay, so basically this one single example will be refreshing all the things that we learned in today's class. So I'll give you a few minutes and then we'll discuss the answer. Once you've got the answer, please to put it in the chat box. Any answers? We'll give you a few more minutes and then we'll discuss. I've got one answer. Like, okay, I'll give you one more minute. Yeah, I understood. Okay. One person have given me the answer. Ajit has answered. Should I wait for like one more minute? Okay, I'll give you. Okay. Yeah. Okay. Slope is 2. Okay. That's what he got. I'll just give you one more minute. So if anybody else want to answer, can take that time. And then we'll discuss the answers. I think this is the last question of this week's. So we have like 5 more minutes to discuss the answer right now. Okay, let's discuss. So first we have to uh, do this calculation for different values of h. So going back to Matlab. So first what we do is the true value is 3 raised to x square. Just a second. It's x cube, right? I'm just Yeah, it's x cube. We have to find the derivative. So that is 3x squared. So x value is 3. The true value, the true derivative is 3x squared. Now we have different values of h, 0.001, 0.01, 0.1 and 1. So what I'm doing is I'm trying to use a for loop so that I can, in every loop, I can take a particular value of h and calculate. So right now I'm just declaring error to be, so what will happen is I have four error values, each corresponding to each h value, right? So for that I'm just declaring a vector, okay? A vector which is having all zeros and the size will be the same size of h. And df also, this is a derivative also I'm saving it, that will also have the same size of h. There are different ways of coding it, I'm just showing you one way, okay? Now the for loop, I'm just looping it over 1 to length of h. So this will loop for 4 times. It will loop from the first index to the last index of h. Now I am just dividing the whole expression into small, small terms so that I don't make any mistakes. So what I do is I take x, then I take x plus h, then I take x plus 2h, and then I put it in the function. Okay. I'm just doing it like step by step. You can do it in one single expression also. That is also completely fine. So I take x, x plus h, x plus 2h. So why do I take hi? Because h is a vector. According to the loop, I will keep changing. So the first loop, h will be taking 0.01. And for the next loop, h will be taking 0.0. Sorry, first loop, it will be taking 0.001. Next loop, it will be taking 0.01. It will be going on like that. Then I'll take the cube of each term. So it will be x cube. This is x plus h cube. This is x plus 2h cube. Then I'll put it in the expression. So this is my final answer that I get. How do I calculate the error? Error is the difference between this answer and the true value. So I got the error here. It has to be the absolute difference. So like this loop will run for the first value of h, second value of h, and till the last value of h. So let me just run this portion. Clear CLC. So this is what I've got. These are the different derivative values, and this is how the error values looks. So error value looks like this. Okay, and this is the differential value. Now what happens is we'll have to plot log of, you have to take the log of h and log of errors and you have to plot it. So yeah, this will be my plot. It is like a straight line, right? And we have to calculate the slope. How do you calculate the slope? So one way is you can just click on this graph. You will be getting the values here, x and y values. So that will be, I'll just calculate the difference. Difference of y value 0.30103 minus minus 5.69897, 5.69897 divided by 0 minus minus 3. We'll be getting 2. Okay, either you can do it directly from the graph, or what you can do is you already know that all the values are here, right? So what I do is I take the log of the last error value and minus log of the first error value divided by log of the last step size minus log of the first step size. Okay, I can do it just by the expression also. So this will compute to, I just ran this code. Now the order will be 2. Okay. So the order of accuracy for this approximation is 2. That is, if I'm if I'm decreasing or increasing h by a factor of 10, my error will be decreasing or increasing by a factor of 100. Okay, so if you want, you can see that error term here. It was 0. E raised to minus 0.6, then it became e raised to minus 0.4. This is e raised to minus 0.2. So this error is changing by a factor of hundreds. Okay, so that is why the order of accuracy is 2. Have you guys understood? Should I explain any part of it again? I hope you have understood and many of you got the answer right also. Really good. So I hope this helped you answer your assignment questions. If you don't have any questions, yes, we'll be ending today's session and we'll see again on next Friday, 6 to 8. Yeah, thank you so much. Yeah, you may leave the session if you don't have any questions. Yeah, thank you all. I'm ending the session right now.